topic. All right, the first derivative test. I'm going to write down the example instruction in the shortest possible form. All right, so problem statement, let me write it like this. Find all relative extrema of this function f of x equal to e to the power 2x squared minus 12x using the first derivative test. Remember, this is how we model that question. For function f of x equal to e to the power 2x squared minus 12x. Number one, calculate the domain of the function. Number two, find all cut points of f prime x. Number three, draw the slope chart, draw the sign chart for f prime x. Then number four, give the intervals where the function is increasing, give the intervals where the function is decreasing, find any relative maxima and relative minima of this function. All right. So that's how we break down this particular question into several pieces. Just to save some space, I'm writing this shorter version of the example. Remember, this is a four-step process, right? Step one, compute the cut points of f prime x. Step two, puncture them from the number line to get the test intervals. Once you get the test interval, pick one test x value from each test interval, check the sign of f prime x. Based on your conclusion, you are going to create that table. And then final step is answer all the questions about increasing, decreasingness, and concavity, and relative extrema. So let's work step by step. Okay, so let me add compute increasing, decreasing intervals. All right. Okay, so let's work step by step. As I said, the goal is to recall the general idea in terms of one quick example. I need to find the cut points of f prime x. These are the candidates for relative maxima and minima. Let's find them out. For that, I will be needing the derivative of this function. Let's find out its derivative. Fairly simple, right? You need to use the chain rule. Let's use it. Derivative of e to the 2x squared plus 12x is e to the 2x squared minus 12x times derivative of 2x squared minus 12x, which is going to be 4x minus 12. All right. Remember how we calculate the cut point of f prime x? We check for two things, right? We set f prime x equal to 0 and we solve the equation for x. And then we set the denominator of f prime x equal to 0 and we solve it for x. It is crystal clear that there is nothing in the denominator. So for me, there is only one way to get the cut points, right? Set f prime x equal to 0. So for cut points, I'm going to set f prime x equal to 0 and my plan is to solve it for variable x. Recall that exponential function is a strictly positive function, right? So in order to make this product 0, you must have that factor equal to 0. E to the power anything is a strictly positive quantity, right? So the only possibility that makes this product 0 is 4x minus 12 being equal to 0. The reason is very clear, because e to the anything, this is going to be strictly positive, right? Let me solve this for variable x. All right, it's a linear equation in x. Pretty easy to solve for x. I get x equal to 3. There's only one cut point of f prime x, and that cut point is x equal to 3. All right. First step is done. Step 2, puncture this cut point from the number line to get the test intervals. So my goal is to cut the number line by this cut point, x equal to 3. You see, whole number line is divided into two pieces. These are two subintervals. Let's create that table. All right, the table consisting, 4 rows. Row number 1 stores the information about test intervals. There are two of them, negative infinity to 3 and then 3 to infinity. I need to pick test x value from each one of them. Let's pick 0 from here, and then let's pick 4 from here. I need the sign of f prime x. All right. As I said, here you can make this computation a little faster. If you already know that e to the anything is a strictly positive quantity, then the sign of f prime purely depends on that second factor, 4x minus 12. Whatever the sign of 4x minus 12 is, that's going to be the sign of the entire f prime x. All right. So let me calculate the sign of f prime x based on the sign of 4x minus 12. Right? Because that is positive, it's not going to play any role in deciding the sign of f prime x. Okay, I'm gonna plug x equal to 0, 4 times 0 minus 12, that's negative. I'm gonna plug x equal to 4, 4 times 4 minus 12, that's 16 minus 12, that's gonna be positive. As I said, we are only interested in the sign. We are not interested in the final answer. Conclusion. Remember, this is a conclusion about our function. Conclusion for f of x. Since the slope is negative, function is decreasing. Slope is positive, function is increasing. All right. If you copy that third row on the number line, you get the sign chart of f prime x. If you copy that fourth row on that number line, what you get is called the slope chart of the function. All right. As I said, pay attention to the wording. This is the sign of the derivative, so sign chart of f prime x. This is the slope of the original function, right? It's a conclusion about the function itself. Okay, the table is complete. We can answer all the questions now, right? What are the cut points of this cut points of derivatives? Well, derivative has only one cut point, and it's x equal to 3. Give the interval where f of x is increasing. So f of x is increasing only on one subinterval, and that's 3 to infinity. F of x is decreasing on the interval negative infinity to 3. All right. Time to identify relative maximum and relative minimum. All right. So f has relative max. F has relative min. And we would like to identify relative maxima and minima. I want you to notice that there is only one cut point of f prime x. There's only one candidate, meaning this one candidate could be max, could be min. If it is max, then there is no min. If it is min, then there is no max, right? We have to apply the first derivative test to check it. How do we apply the first derivative test? We check the slope chart, and we check whether our function changes from decreasing to increasing or increasing to decreasing. If it changes from decreasing to increasing, then we have a minimum value. If it changes from increasing to decreasing, we have a maximum value. All right. Look at the slope chart. Function changes from decreasing to increasing. This must be relative minimum. All right. So function has a relative minimum at x equal to 3. All right. That means there is no relative maxima. There was only one cut point. We classified it as a minimum. So relative maximum is none. Right. Okay. If you want your answer in form of x comma y format, plug x equal to 3 into your function. Look, f at 3 is going to be e to the power 2 times 3 square minus 12, 12 times 3, and this is going to be e to the 18 minus 36, looks like e to the negative 30, negative 18 is what we get, right? Relative minimum in x comma y format would be, 3 comma e to the negative 18. Again, read the instruction carefully. Some problem may ask you only for x value, for relative minimum or maximum. If it only asks for x value, you would just stop there. If it says give the relative maximum in format x comma y, then you have to compute the corresponding y value by throwing that x value into the original function, right? So this is the computation of relative extrema using the first derivative test. Remember, we have two different tests to classify the nature of the cut point of f prime x. The second test that gives us the same information is called the second derivative test, right? This is the fastest way to classify if the cut point of f prime is max or min. As I said, even though it's the fastest way, it comes with some price, right? And the price is very clear that second derivative test is weaker compared to the first derivative test. Why is it weaker? Because the second derivative test only gives us an opportunity to identify the nature of those cut points that are coming by setting f prime x equal to 0. The cut point of f prime that we get by setting the denominator of derivative equal to 0 cannot be handled using the second derivative test. So this is a limitation of second derivative test. So let me write down the question here. So let's say we work with the same function. Find all relative extrema of this function f of x equal to e to the 2x square minus 12x using the second derivative test. Remember, this is a three-step process, right? Step 1, find the cut point of f prime x, meaning step 1 is identically the same as the first derivative test. You need to find out what are the candidates for relative maxima and minima. So find the cut points of f prime x. Step number 2, compute the second derivative of your function, right? And then step number 3, one by one, throw the cut point of f prime into the second derivative, check the sign of the outcome, and based on the sign, decide whether your function has max or min at the cut point of f prime, right? So as I said, the first step is identically the same. So I'm not going to write down that first step again. This is exactly the same computation. I will just say directly that step 1, cut points of f prime x. I only have one candidate and x equal to 3 is that candidate. Okay. Step 2, I need to compute the second derivative of the function. All right, let me write down the first derivative here. The first derivative was 4x minus 12 times e to the 2x square minus 12x. All right, so this was the first derivative, first order derivative of that function. I need to find out the second order derivative. Let's compute it. I must use the product rule. This is a function viewable in form of factors, right? Let's use the product rule. First factor as is times derivative prime of the second factor plus second factor times prime of the first factor. All right. Think about it, how to get rid of those two prime notation. To get rid of this prime notation, you'll have to use the chain rule form of exponential function. To get rid of this prime notation, just use the constant rule and the power rule for differentiation, right? Let's do that. I'm going to differentiate this. I get 4x minus 12. Chain rule gives me e to the 2x square minus 12x times 4x minus 12. Right, that's the derivative of that exponential part using the chain rule. And then I have e to the 2x square minus 12x. Derivative of 4x minus 12 is just 4, right? I want you to notice that there are two copies of 4x minus 12 in the first term. I can write it as a square of 4x minus 12. Then I have e to the 2x square minus 12x. And then I have 4 e to the 2x square minus 12x. This is the second derivative of the given function. All right. How do we use the second derivative test? We throw the cut point of f prime x into the second derivative. We observe the sign, and based on the sign, we are going to make a decision whether it is relative max or min or nothing. Right? Let's do that. So here is the final step. I'm going to throw x equal to 3 into the second derivative. Look what do we get? 4 times 3 minus 12. So this is basically 12 minus 12. And it is 0, right? 0 multiplied by anything is 0. 2 times 3 square minus 12 times 3 plus 4 e to the 2 times 3 square minus 12 times 3. Do this computation carefully, right? As I said, it is clear that this entry is 0. 0 multiplied by anything is 0. So that entire thing turns out to be 0, right? So I'm left with only that second term, which ends up being 4 e to the power. This is 18 minus 36. So this is really 4 e to the negative 18. All right, I recommend you guys to change that negative exponent into positive exponent. We just wanted to make sure that what is the sign of this second derivative at 3. Looks like this is same as 4 over e to the 18. It is positive. All right. What do we mean by second derivative being positive? If second derivative is positive, the graph of the function is concave up, right? And that means you must have a minimum value right there. All right. By the second derivative test, we can say, so f has relative minimum at x equal to 3. All right. Because the second derivative takes positive sign, graph is concave up, meaning at cut point of f prime, the function must have a minimum value. Again, check both of these problems carefully. You will have both of these techniques on your exam. So be sure you guys know how to use this idea. This is a 4-step method. This is a 3-step method. Both does the same thing. It let us identify relative extrema of the given function. All right. First derivative test is stronger because it allows us to deal with any type of cut point of f prime x. The second derivative test, it's a weaker version, but still, it is applicable on a particular set of cut point of f prime x. All right, so this is the first two topics. Let's move on and let's recall the idea of computing concavity intervals and inflection points. Basically the same four-step method, the only difference is we are going to work with the cut point of the second derivative, which appears to be the candidates for the inflection points, right? So let's do that. Let me write down the instruction first. So here is an example. Let's say find all inflection points and determine concavity intervals for this function f of x equal to, let's keep it simple, x cube minus 3x square plus 4x plus 5. All right, so we started first example in terms of exponential function. Let's keep things simple here. As I said, goal is to recall the four-step idea to compute concavity intervals and inflection points. I'm going to first compute cut points of the second derivative. Then I'll puncture the number line by the cut point of the second derivative. I'll create the table and then I'll answer all the questions. These are the four steps that we need to follow. Let's do that. Here is the first step in our solution. To compute the cut point of the second derivative, I first need to work out the second derivative of this function. This is a polynomial, pretty easy to differentiate, right? 3x squared minus 6x plus 4 is the first order derivative. Second order derivative is going to be 6x minus 6. For cut points of the second derivative, you need to set the top and bottom of f double prime x equal to 0. There's nothing in the denominator, right? The only way to get the cut points of the second derivative is by setting f double prime x is equal to 0. Set it equal to 0, solve for x. Looks like we only get one cut point. This is the only candidate for possible inflection points. All right. Again, I keep using the word candidate because we are not sure whether the concavity will be changed at this point or not. For that, we need more analysis. So here is the second step. I'm going to puncture the number line by the cut point of the second derivative. Two subintervals I got. I'm going to create that table with 4 rows, right? Test intervals in the first row, negative infinity to 1, and then 1 to infinity. Pick test x value, maybe 0 from here, 2 from here. I need the sign of the second derivative. The second derivative of the function is 6x minus 6. All right. And then last row is for conclusion for the function, conclusion for the original function, right? I'm going to plug x equal to 0 here. 6 times 0 minus 6 is negative. 6 times 2 minus 6, so that's 12 minus 6. 12 minus 6 is positive, right? If second derivative is negative, function is concave down. If second derivative is positive, function is concave up. If you copy the third row on the number line, you get the sign chart for the second derivative. Again, as I said, pay attention to the wording, sign chart of the second derivative. This is how the sign of the second derivative changes on the number line. To get the concavity chart, you copy the fourth row. On the same number line, you get concavity chart of the original function, right? So this is an application of derivative in terms of function, right? So we realize that function can be understood using the derivatives, right? If sketching graph of the function is complicated, we can always use calculus to answer this type of questions, right? Questions about increasing, decreasing mass, concavity, inflection point, so on and so forth, right? Okay, we can answer all the questions now. The cut points of the second derivative, x equal to 1. Concavity chart right there. Sign chart of the second derivative is also there. Function is concave upward only on one interval, 1 to infinity. Function is concave downward. That also happens only on one interval, negative infinity to 1. F has inflection point. Check the concavity chart to verify if concavity is changing or not. Looks like function is becoming concave up from concave down, right? So it is concave down before in the region negative infinity to 1, and then it becomes concave up on the region 1 to infinity. Concavity for sure is changing, right? Meaning that 1 is genuine inflection point. All right, x equal to 1 is the genuine inflection point. If you want inflection point in form of x comma y, plug x equal to 1 into your function. Right, let me do that computation too. F equal to 1 gives me 1 minus 3 plus 4 plus 5, and that is going to be 7. The inflection point on the graph must be located at x value 1, y value 7. All right. So this is how we compute concavity intervals and certainly, inflection points. Now let's move on and let's recall the idea about absolute extrema. I would like to give you one quick example here on how to compute absolute extrema of the function. Compute absolute extrema or absolute maxima and minima for this function f of x equal to, let's say we work with x cubed minus 12x squared plus 2 on the region, or maybe let's say okay, on the interval, let's say negative 1 to 2, negative 1 to 3. Okay. All right. So remember, the idea is very simple. We want to find out the highest value of the function, highest value of this function on that restricted region. All right. So this relative maxima and minima, they are local maxima and minima, and they are maxima and minima in the small region. We are trying to find out the winner value of the function and the loser value of the function on the region negative 1 to 3 only. So whatever the graph of this function is, I would like to find out the highest value of the function and smallest value of the function on this interval only. Let's try to answer this question. As I said, this is a 3-step process only. All right. Actually 4-step process. Step 1, compute the cut points of f prime x. all right, and remove all those cut points that are outside the region, -1 to 3. Once you get the cut point of f prime x, in the second step, you are going to do the evaluation, right? Evaluate your function at the left and right endpoint. In step 3, evaluate your function at good cut point of f prime x. When I say good cut point, I really mean the cut points that are residing in this region of interest. And then step 4 is the final step. Pick the highest value from step 2 and 3, label it as absolute max. Pick the smallest value, label it as absolute min. Quite a few of you are very clear that this is going to be the easiest problem on your exam. Let's try to apply this 4-step method to solve it. All right. So here is the solution. I will compute the cut points of f prime x. So step 1, computation of f prime x. These are the candidates for maxima and minima. Derivative will be 3x squared minus 24x. All right, looks like we need to make a minor change in the function. Okay. I just wanted to make sure that we end up getting nice numbers. All right. So let's do x cubed minus 6x squared plus 2 on the region -1 to 3. All right. F prime x is going to be 3x squared minus 12x plus 0. All right. So this is what we get. How do we find the cut points of f prime x? For cut points, we are going to set this equal to 0. And then we will, solve this equation for x. Looks like I have two choices for x equal to 0 and x equal to 4. All right. I want you to notice immediately that x equal to 4 is outside the region of interest. X equal to 4 is not inside the region. So I'm going to throw this. I will simply say this is not in interval 1 to 3. Since that's not a part of the region of interest, that cannot be absolute max or min. Okay, so that point is out of the game. Step 2, I'm going to evaluate my function at -1 and at 3. Let's do that. Plug x equal to -1. -1 cubed 6 times -1 square plus 2. That's -1 minus 6 plus 2. I end up getting -5. All right. Let's do the same thing. I need to plug x equal to 3 in here. 3 cubed minus 6 times 3 squared plus 2. This is 27 minus 54 plus 2. Looks like we get -25, right? Step 3, evaluate your function at the good cut point of f prime x. Good cut point is 0, right? Evaluate your function at 0. 0 cubed minus 6 times 0 squared plus 2. That's going to be 2. 3 steps are done, right? Between step 2 and 3, pick the highest value. Call it absolute max. Pick the smallest value. Call it absolute min. Let me write down that answer in the 4th step. Absolute max in x, y format. Look, it occurs at input 0 with the value 2. So 0, 2. Right? X, y format is already there. We have evaluated function itself at those points. Absolute min in x, y format, it's going to be 3 comma negative 25. Done, right? So again, as I say, this really will be the simplest problem on your exam. You don't want to miss that problem. All right. Okay. Then we get into the application of extremas. I would like to remind you, we have done many different types of problems in terms of application of extremas, right? If you remember, we discussed the example creating a rectangular pen with um, one side of fencing not needed. We created an example involving a rectangular pen with 2 or 3 parallel sides to its width. We also learned the example in terms of creating a box by cutting squares of the equal size from each corner and folding the sides upward, right? Would like to show you one quick example similar to one of those problems, right? So most of the problems that we discussed, we maximize, particular quantity. For example, in those rectangular enclosure problems, we try to maximize, the captured area, right? So let's try to construct something in form of a minimization problem. Okay, so here is the example we would like to solve. Let's say a box with the square top or square bottom is to be constructed to hold, let's say, 1000 cubic centimeter material. All right. So my goal is to create a rectangular box which has a square base. All right. So here is a box. Picture of the box. As I said, we would like to create the box with a square base, right? So square base means the base will have height and width the same. All right, and I'm going to denote that width and length of the base by variable x. Okay, we want to create a box that can hold 1000 cubic centimeter of material. All right, so this is the first statement in the problem. Okay, the second statement will be about optimization. All right, find the dimension of this box that minimizes the surface area. All right, so find the dimension of the box that minimizes the total surface area. All right, let's think about it, this statement. Surface area. How many surfaces does a box have? The box really has 6 surfaces, right? Look at this. 2 surfaces, one surface is in the bottom, the base itself, one surface is in the top, right? So in the top and the bottom you have 2 surfaces, and then on 4 sides you have 4 more surfaces. Altogether, this box has 6 different surfaces, right? Minimizing surface area would really mean using this less amount of material to create a box. All right. If you use less amount of material to create the box, it will minimize the production cost. If production cost is minimized, then the profit is max, right? So I want you to see this question in form of a very simple and nice application. Suppose you have a cardboard and you wanted to create a box from the cardboard that holds certain amount of material. And let's say we have a limited amount of money, right? So we wanted to create such box using the minimum amount of material from the cardboard. All right. As I said, it's a practical question, right? Let's try to answer this question carefully. Okay. The box has 3 dimensions: height, width, and length. Okay. Look, height, width, and length. Because the base is square, I am going to use variable x to represent height, length, and width for the box. For the height, let's use other variable y. All right. So I'm going to start the solution by simply labeling those parts. Let width and length be x unit. All right, and height be y unit. All right. So as I said, I got this impression from the fact that the box has a square bottom or square base. All right. Square base means it will have the length and width the same for the base. Okay. So as I said, we solve this problem in 7 simple steps. Right. Step 1. Read the problem carefully and understand what is given and what you need to calculate. 2 things we are looking for: the expression that we would like to maximize or minimize, and then the given information in terms of variables that we have used in the picture. Draw the diagram if possible, label the variables, right? And then step 3, write down given information and minimization problem. Step 4 is the most important step. Using the given information, convert minimization problem into function with one variable so that we can use calculus. Once you have function of one variable, it's a game over type of situation. Compute the cut point of f prime x, use the second derivative test to check if at cut point of f prime you have a max or min, and based on that you convert your findings into the solution of the original problem. So these are the 7 steps that we need to apply carefully on this example. So as you see, I finished the first 2 steps. I read the problem carefully and then I assign the variables in the picture itself. All right. Let's find out, what do we want to maximize or minimize. We want to minimize the total surface area. So we want to minimize surface area. There are 6 surfaces, right? What's the area of what are the shape of these surfaces? First of all the surfaces, all 6 surfaces, they are either square or rectangles, right? Do we know how to calculate area of square or rectangle? Answer should be yes, right? Area of the rectangle is length times width. Area of the square is length times length, right? So this is what I would like to do. I want to minimize surface area. There are 6 surfaces. Area of the base is x times x. Area of the top surface is also x times x, because bottom and top, they are of the same area. And what's the area of these 4 surfaces, right? The area of this particular surface is going to be x times y. Same way, area of the other one will be x times y. We have 4 of them, right? So I have x times y, x times y, x times y, x times y. Understand that this is the area of all 6 surfaces, right? There are a couple of like terms. I'm gonna add them 2x squared plus 4xy. This is what we would like to minimize. All right. What is given? It's given that the box will be able to hold 1000 cubic centimeter of material, meaning the volume of the box is given, right? Volume of the box is given. How do we find out the volume of the box? Well, multiply length, width, and height. All right. So let's write this down. It is given that the volume of the box, which is x times y, equal to 1000, right? Or this is same as x square y equal to 1000. All right. So as I said, we are looking for two things: the expression that we would like to maximize or minimize, and then the given information, and we got both of them. All right, this is the mathematical way to write down those two lines, right? This line reads as, the box can hold 1000 cubic centimeter of the material, and this should be read as we wanted to minimize the surface area. There are 6 surfaces. I add all 6 areas together. I want the result to be minimum. All right, let's try it. As I said, the most important step here is to use the given information to convert this into function of one variable. I have x and y both. I want to eliminate one of them. This is what I'm going to do. I will use the given information, solve this for variable y in terms of x, and plug this into your minimization problem, right? So I would like to find out the minimum of 2x squared plus 4xy. As I said, I'm going to replace that y by 1000 divided by x squared. All right, and I can label this as a function because there is only variable x there. Y is not in the expression anymore. You can simplify this a little bit. 2x squared plus 4000 over x. This is your function. Time to use calculus. All right, so as I said, the most trickiest part in this computation is to convert your problem into a function of one variable using the given information. All right, so be sure you guys know how to do that. We are solving the given information for one variable and plug its value into our minimization expression to get the function. Now let's use the calculus. Second derivative test example, right? So if I ask you to use the second derivative test to find relative extrema of this function, how would you do that? Let's check. All right, so I will find out f prime x. Derivative of 2x squared is 4x. Derivative of x to the negative 1 is negative 1 x to the negative 2. Right, so negative 4000 over x squared is what you are going to get. How do we find the cut points? Remember, since we are using the second derivative test, I'm only going to set f prime x equal to 0. I get 4x minus 4000 over x squared equal to 0. I get 4x equal to 4000 over x squared. Let's simplify this. Send this x squared over the other side. Looks like I get x cube equal to 4000 over 4, and this is going to be 1000. Do we know cube root of 1000? Well, answer should be yes. Cube root of 1000 is 10. We erase this picture. All right, this means x must be 10 units. All right, we still don't know whether x equal to 10 is going to maximize or minimize our function. So what I'm going to do next is, I will use the second derivative test. Compute the second derivative of this function. All right, find f double prime x. Do this carefully. Derivative of 4x is 4. And derivative of x to the negative 2 is negative 2 x to the negative 3. All right, negative 2x to the negative 3. That really gives me 4 plus 8,000 over x cubed. All right, what do we want to do? We need to throw the cut point of f prime x into the second derivative. And we need to observe the sign. Again, as I said, I am not interested in the final answer. I am only interested in the sign. Second derivative at the cut point of f prime is positive, meaning the function has relative minimum at x equal to 10. Understand that this is the second derivative test example. Nothing else. We already did one with exponential function. This is the second one, right? Okay, so function has a relative minimum at x equal to 10. We got our answer. Function is minimum, meaning that is minimum when x is 10. But that represents the surface area of all 6 spaces of, the box. So, time to convert this information into the solution of the problem. So, x represent length and width. And it's going to be 10 centimeter. All right. The length and width of such box needs to be 10 centimeter. What should be the height? Let's find it out. To compute the height, you will have to plug your x value in the relationship between x and y. We already got that relationship to get the function, right? So let's compute y. Y is 1000 divided by x squared. 1000 divided by 100 is just 10. So we are saying that if we choose to make a square box, the box with height, length, and width exactly the same, then it will hold 1000 centimeter cube of material, as well as the production cost will be minimum, right? Surface area is minimum means production cost is minimum because less material will be used to create such box. All right. So these are the dimension. Length, width are 10 centimeter and height is 10 centimeter as well. As I said, I recommend you guys to check class notes to see more interesting set of problem based on this idea. It's really a simple strategy. We convert these wordings into mathematical statement. 2 things we are looking for, things that we would like to maximize or minimize, and the given information. Once you have both of them using given information, you get function of x. And then once you get function of x, you have a very well designed way. Use the second derivative test to find relative extrema. And then based on your findings, you convert your answer, relative extrema, in form of answer to the original problem. All right. Now let's move on and let's talk about implicit differentiation and related rates. This is also a very simple and clean idea. So let's recall both of them one by one in terms of a couple of examples. Okay, so here is an example. Let's say find dy by dx for this function. Let's say we have 2y e to the x square minus 1 plus 2x plus or plus 2y equal to 2x square plus 3y square minus 2, and evaluate dy by dx at 0, 1. All right, when or 1, 0. All right, when x is 1, y is 0, I would like to evaluate the derivative of the function. Remember, what is implicit function? Implicit expression or implicit function is the one, is the expression that are hard to solve for variable y in terms of pure function of x. All right, these are the expression that we are unable to solve for y purely in terms of x. The question is, can we find out the derivative? Answer is yes. How do we find out the derivatives? Well, use the basic differentiation rules, but keep in mind that you will be treating y as a function of x, right? So let's try it. Here is the solution. First and foremost, decide what rules are you going to use to differentiate every single term on both sides. And once you select the rules, you apply them, right? Okay, let's do that. This is how I'm going to read it. 2 times function of x times e to the x square minus 1. Clearly, this first term is in form of factors, something of x multiplied by expression involving x. So I must use the product rule to differentiate the first term, right? This is a simple derivative, 2 times function of x, simple derivative with respect to y, with respect to x. All right. 2x square, I'm going to use the power rule to differentiate it. And then 3 times function of x square. When you have function of x square, meaning this is the expression with 2 layers, right? So chain rule here. And then this is constant, right? So constant rule to differentiate that last term. All right, we have decided what rules are we going to use to differentiate every single term here. Let's go ahead and use that. All right. So again, pretty simple idea. We are going to treat y as a function of x. If you remember, starting from this section, we started using the notation dy by dx. I strongly encourage you guys to use dy by dx notation instead of prime notation, right? Prime notation has its own advantages. Here, because there are too many expression involving y there, I would not really use y prime to represent the derivative. All right, so instead I'll use d by dx notation. Let's do that. Do the setup of the product rule. Look, first factor times d by dx of the second factor plus second factor times d by dx of the first factor. Remember, if constant is multiplied by expression involving x, then we don't touch the constant. So if you want to keep 2 outside, that's fine too. All right. This is the setup of the product rule for the first term. What is the derivative of 2y with respect to x? You would say 2 times d by dx of y. All right. On the other side, derivative of 2x square is 4x. Derivative of 3 times y to the 2. You must use the chain rule. Function of x to the power 2. This must be the inner layer. 2 is the outer layer. How do we differentiate it? Bring 2 in the front. reduce one power of the inner layer, and then multiply it by the derivative of the inner layer with respect to variable x. Notice instead of using prime notation, I am using d by dx. That's the only difference, right? And as I said, you guys have practiced many problems, so now it should look this should not confuse you. Derivative of that constant is just 0. All right. Think about it, how to get rid of those derivative notation. To get rid of this derivative notation, I must use the chain rule form of exponential function. I'm gonna bring the constant out. Derivative of y with respect to x is dy by dx. We only have a symbolic way to represent the derivative of y with respect to x. This is also dy by dx, and that part is also dy by dx. Let's do that. I get 2y e to the x square minus 1 times 2x. E to the x square minus 1 times 2 times dy by dx plus 2 dy by dx equal to 4x plus 6y dy by dx. How do we solve this for dy by dx? Well, to solve it for dy by dx, you need to isolate dy by dx terms, right? I'm going to send this dy by dx term on this side, and then at the same time, I'm going to move that first term that doesn't have dy by dx onto the other side. Obviously, I'll multiply those two numbers. So let's do that. I have e to the x square minus 1 dy by dx times 2. So I'm going to write that 2 in the front, plus 2 dy by dx. And then I'm subtracting 6y dy by dx from both sides. On the other side, I have 4x. And then, as I said, I'm moving this thing over to the other side. So minus 4xy e to the x square minus 1. Our goal is very clear. We wanted to factor dy by dx out. Let's factor it out. 2e to the x square minus 1 plus 2 minus 6y dy by dx equal to 4x minus 4xy e to the x square minus 1. Divide both sides by that bracket inside quantity. 4x minus 4xy e to the x square minus 1 over 2 e to the x square minus 1 plus 2 minus 6y. This is the derivative of the implicit equation with respect to variable x. Again, this is also going to be a very simple example on your exam. Understand that we choose to use d by dx notation for a reason. We don't want to mix that prime notation with the power of y. We are using powers of y as well, right? I don't want to mix it with the power of y. That's why we use that d by dx notation. I need to evaluate this at 1, 0. Let's do that. dy by dx at 1, 0. Put x equal to 1, y equal to 0. 4 times 1 minus 4 times 1 times 0 e to the 1 square minus 1 over 2 e to the 1 square minus 1 plus 2 minus 6 times 0. All right, looks like this is 0, this is 0. E to the 0 is just 1, so I have only one term that survives in the top, and that's 4. In the bottom, I have two terms survives. E to the 1 minus 1 is e to the 0. E to the 0 is just 1, right? So bottom, I have two entries that survives, two copies of 2. Again, this is a pure accident that I end up getting 1. Doesn't have to be 1, all right? Once again, this is a randomly created example. You can create your own example and ask the same question, right? Suppose there is an equation that we are unable to solve for y in terms of pure expression of x. Such equations are called implicit equations. The way to solve implicit equation is pretty simple and straightforward. You select particular rule that you need to apply to differentiate every single term, differentiate them, isolate dy by dx terms by the equality, factor them out, and then send the bracket inside quantity onto the other side. All right? Okay, now let's move on and let's recall related rates in terms of one quick example. All right? I would like to discuss that, famous ladder problem. And then we will discuss one example of Newton's method to end our discussion for today. I will create a short video of 20-25 minutes on integration techniques, and I'm going to post it by the end of the day on our stream channel. I want you guys to check that video, which will complete the entire review for this 1325. All right, let's discuss this example. I'm not going to write down the statement of the example. Instead, let me say it carefully. Let's say a 25 feet ladder is leaning against the wall. All right, so suppose the bottom of the ladder is slipping away from the wall, from the supporting wall. The top is going down, right? So there are two distances that are changing here. The distance between the bottom of the ladder and the wall is increasing. At the same time, distance between top of the ladder and the ground is decreasing. So there are two distances that are changing. I'm simply going to label them by the variable. So suppose the distance between bottom of the ladder and the building is x unit, and distance between the top of the ladder and the ground is, let's say, y units. All right, and the length of the ladder is 25 feet. Let me give you some information. All right, so here is the problem statement. A 25 feet ladder is leaning against the wall. Suppose the bottom of the ladder is sliding away from the wall at the rate of 3 feet per second. So every second, this portion is going 3 feet away from the wall itself. All right. Find the rate at which the distance between top of the ladder and the ground decreases at the instance when the bottom of the ladder is 16 feet away from the wall. All right. So again, understand, find out dy by dt at the moment when x is equal to 16. All right. So whenever you see the right triangle, the first equation that should come into your mind is the Pythagorean identity. Right? What does Pythagorean identity says? It says sum of square of the sides creating the 90-degree angle, it is same as the square of the remaining side. All right, that remaining side is constant in our example. Doesn't have to be constant. You can consider a situation where all these three sides, all these three distances, they grow at the same time, and let's say this triangle becomes larger and larger. All right, again, we just wanted to keep the things simple and more realistic, so that's why we consider that problem. As I say, this is really very famous problem, right, that everybody likes. All right, these two distances are changing over the time, so I would go like, differentiate this with respect to t, differentiate this with respect to t, chain rule, and constant rule. 2x dx by dt is the derivative of this entry. 2y dy by dt is the derivative of that second term. Derivative of 25 is 25 square is 0. All right. This is the relationship between the variable x, y, and their derivatives with respect to time. Very carefully, think about it, what's given. Looks like dx by dt is given, x is given, dy by dt I need to compute, but for that I must know the value of y. All right, so there are 4 unknowns. Out of them 2 are given. I am asked to calculate dy by dt, but to calculate dy by dt I must need the value of y. Let's compute the value of y. I already know how x and y are related to each other. So if x is given, I can solve for y. Let's do that. I'm going to do this on the side. X square plus y square equal to 25 square. All right, so x is given 16 square plus y square equal to 625. 16 square is 256. Let's subtract 256 from 625. All right, so I get 1 and then 6, 3. All right, so looks like I have selected incorrect numbers. All right, let's keep x equal to 20 feet. All right, I just wanted to end up getting creating nice numbers. All right, so change that x to 20. All right, I get 20 square plus y square equal to 25 square. All right, this is 400 plus y square equal to 625. So y square must be 625 minus 400. Y square is 225. This means y must be 15. Again, we wanted to produce a nice number as an output, so that's the reason why I made that little change in our problem. Okay, so I got y equal to 15. Remember, being a distance, it's a positive quantity, right? So I now know x, y, dx by dt. I can solve for dy by dt. Let's throw the values in. 2 times 20 times 3 plus 2 times 15 times dy by dt equal to 0. We can solve this for dy by dt. 120 plus 30 dy by dt equal to 0. So we get dy by dt equal to negative 120 over 30. Negative 4 is what we get. All right, what does this mean? This means the distance between top of the ladder and the ground is decreasing at 4 feet per second. Remember, if you use the word decreasing, then no need to use that negative sign. Very important thing. All right, that negative sign means the distance is decreasing. Okay.